All right, so my audio is rolling now. We're trying to get this live stream set up. Um, don't look at the sun with your eyes. So it's weird on. Well, hopefully you guys can see the sunspots.
There you go.
Um, the yeah, turn on that, or we're gonna get feedback. um, at least I don't know if my live stream quality is good enough. It might not be like 1080p. It should be, but there's a if you can see it, there's a sunspot kind of in the lower middle, and then on there's another one on the right. And so, a couple of things about these I was gonna share. The, I'm pretty sure the one on the right there, that's just on the edge of the sun, is turning into view. Pretty sure right now we're getting a mirrored image because of the way my telescope works. So that is, if you were to look at the sun, it's actually on the left side, not the right. Actually, I have some eclipse glasses. I'm gonna see if I can see it. Um, it's hard to see without the telescope. They're pretty small. But actually, it might be flipped both ways, upside down and left to right. I'm not sure. Anyway, so the sun apparently rotates like on its axis every 25 days, I believe it is. And so, a couple weeks ago, we had some auroras from the sunspot, some big CMEs that came off of that sunspot, and that energy hit our magnetic field on Earth and caused the colorful auroras, which I got to see. It was really cool. Um, and now the same sunspot is turning back into view. It's there on the edge, so we probably have another week or so before it's facing towards Earth, and we could potentially get some more auroras if it's still active by the time it's facing us, and if it emits some CMEs. So that's something to look forward to. Maybe we can see the aurora borealis again. So right now I am using a 130 millimeter telescope with a 25 millimeter eyepiece. So what that means is the magnification, I think, I don't do math very good, but according to the internet, the calculation is hard to understand. So, no, I'm just kidding. It's pretty simple. I think you just like divide one by the other, and that tells you like the how much zoom you are. In this case, it's a 26 times zoom. I'm losing the sun. Come back. It's slowly moving. Um, there we go. So, what is that the calculation? Focal length is typically provided or can be calculated based on the focal length of the telescope. In my case, that's 130 millimeters. And then the eyepiece, it gave me a, what's the formula? Let me see. Magnification equals focal length divided by, of the telescope divided by the focal length of the eyepiece. I don't know why it's giving me that in weird notation that I can't understand, but I think that's what it is. Anyway, so on my camera, I can see a few sunspots. There's one on the edge, one in the middle, and a few smaller ones, like even more in the middle, like center middle, instead of the bigger one that's in the lower middle. Kind of cool. Um, all right. So, oh yeah, we were just talking about differential rotation, which is something I just learned about. And apparently, get a load of this, the sun does not all rotate at once. I thought that was crazy. It kind of makes sense because the sun's not a solid rock like the Earth, right? I mean, the Earth has water, but basically, what this differential rotation means is the, what do you call the middle again? The equator, the equator of the sun spins, I think, faster than the poles of the sun. Let me double check. I was just looking this up. So the sun takes approximately 25 to 35 days to complete one rotation. I was like, wait, why is there a range there? It depends on the latitude. At the equator, it rotates approximately every 25 days, while at higher latitudes near the poles, it can take 35 days. This variation is due to the sun's differential rotation, meaning different parts of the sun rotate at different speeds. And I guess that's just because it's like gas, right? So it's like, it's not all one body. It can move at different speeds. And it is this which causes, or at least this is partially what causes the the magnetic field in the sun. So all these moving particles, that creates energy, which gets, I don't know exactly how it works, but that's what creates the magnetic field. And those magnetic fields, there's other things that affect it, I believe, and that just variation in that creates these sunspots, and then they can, wow, it's really bright. And then they can get irritated or whatever you want to call it and unleash solar flares and CMEs. So, fun fact for you. Yes, you, back. What's your question?
So you said that light will, if the flares are still active in about a week, we'll probably see them. Why?
Yes, good question. Great, thanks for asking.
Yeah.
So Katie's question was, why? Well, I was telling her that the solar the sunspots. Let me move this a little bit before I finish answering. Um, by the way, guys, I'm no expert. I just googled this, so that's where we're at. The sunspots that caused the big the big aurora borealis a couple of weeks ago is this particular sunspot which rotated out of view. And that it's near the equator, so it should take approximately 25 days for that to rotate back towards Earth again. Um, just the other day, it had a big CME. Well, maybe I think it was a CME, yeah, not just a flare. Like actual plasma from the sun was ejected, but it wasn't facing towards Earth. It flew off into space. So in about a week or so, that sunspot will probably be aimed at us. And if it decides to shoot, pull the trigger while it's aimed at us, then we will get a lot of that CME and cause the aurora borealis. And maybe it can have other effects, right? Like it can actually affect GPS systems. And um, in history, I read about this one CME that hit Earth right after like the telegraph and like the telephone line. I think it was just the telegraph. That was the most advanced technology at the time. And it was like so strong that it actually caused energy to be in the telegraph lines, even though they had powered it down. And so you could still send, I guess Morse or whatever, what do you call that? A telegraph. You could still send, they could still send telegraphs because the poles were being charged by the CME, the sun.
Cool.
I know, isn't that crazy?
That's really cool.
So
So it's just the specific flare that's strong enough to like affect her.
yeah, I mean, like strong enough. Like the poles will get it more often. They can get any sort of energy. I suppose can cause the aurora at the poles, but if you get one that's strong enough and that actually hits Earth, that's when there's extra energy to bring the aurora down to southern or more mid latitudes. Yeah. So that answer your question?
Yes. What's CME?
CME stands for coronal mass ejection, which, because the corona, I guess, is the outside of the sun. Is that right? I don't know. Yeah, I'm not sure about that. Yeah, double fact check that. I'm pretty sure the sun does have different layers and stuff, but the sunspots, I found out, are actually areas of cooler. They're not as hot as the rest of the sun. I don't know why they cool down. I don't know why that works, but well, the CMEs come from the sunspots, but yeah, that area where they originate from is apparently a cooler area. It'd be interesting.
Why they flare? Because maybe the cool area, the hot hits it, and it.
That could be, yeah.
I guess it's.
I think the reason the CMEs leave the sun is because, like I saw a little animation of it once. The magnetic field is usually depicted by like these lines, at least for when I've seen it. And so they move, and sometimes they like create little circular shapes or like C shapes. And if they get strong enough, they like will close off and snap. And so it'll like realign, but then the starch that got snapped off then leaves. So I think it's because of the magnetic field, but
Okay.
that I'm not sure about. That
No,
would,
that makes sense.
yeah,
And it is coronal mass ejection, a significant release of plasma and magnetic field from the solar corona.
from the solar crown. Yeah. So, and I guess that's Spanish for crown, so that would make sense. That's like the outside or the edge. Yeah. Cool.
Okay, so there's 6 layers of the sun.
6 layers of the sun. Okay, what are the layers?
The layers are the core,
The core.
radiative zone.
Okay, the radiative zone.
Do you want me to tell you what they are, or just
Does it?
what
Do you
they
have
do?
definitions? Yeah. What's the so? What's the core? What stands it apart?
The core is the center. The central region where nuclear fusion occurs, producing the sun's energy. Temperatures can reach about 15 million degrees Celsius.
Wow.
The radiative zone surrounding the core, energy produced in the core is transferred outward by radiation. This zone affects from about 25% to 70% of the sun's radius. The convective zone, about the radiative zone, energy is transported by, I can't read that word, convection.
Convection.
I see
Okay.
it, it's what throws me off. Hot plasma rises, cools as it nears the surface, and then sinks back down to be reheated and rise again. So that's where you get our spots that get cooler.
Okay.
The photosphere, the visible surface of the sun.
Wait. So it's the sun is hotter. What was the last part? The sun is hotter in the inside, and then
So hot plasma rises, cools as it nears the surface, and then sinks back down to be reheated.
oh. Okay, so the edge of the sun is cooler, and that makes sense because hotter rises, and then as it gets away from the really hot inside, it's comparably cooler, but it's still seriously hot. But then that allows it to sink. Okay.
Then the photosphere, the visible surface of the sun from which light is emitted, it has a temperature of about.
I like that, the photosphere. Okay.
Is about 5,500 degrees Celsius, and is the layer we see with our eyes. Don't look at the sun though.
Yeah.
Without glasses.
But I'm guessing also this layer we're seeing with the telescope, this is probably the photosphere.
Yeah.
And this is layer number 4, or what are we at?
Yes, that's 4.
That's 4, okay.
The 5th layer is the chromosphere. Above the photosphere, this layer appears as a reddish glow during solar eclipses.
Mm-hmm.
It is a few thousand kilometers thick and has a temperature ranging from 4,000 to 25,000 degrees Celsius.
Wait, did you say a few thousand kilometers thick?
Uh-huh.
Okay,
A few thousand.
that makes sense.
So here's the crazy part. Before I go to the 6th.
Okay.
Is that the sun is so big that the inside. Okay, so that fifth layer is about 4,000 to 25,000 degrees Celsius.
And that's the coolest part.
Yeah, the core is 15 million degrees Celsius.
15 million degrees Celsius
Compared to 4,000.
compared to 4,000.
25,000. So that's how big is that the temperature can range.
That's a huge difference too. Yeah.
It's a huge difference.
Oops.
So maybe the core is just extra small. I'll ask.
Yeah.
Okay. So then the 6th layer is the corona, the outermost layer extending millions of kilometers into space. It is visible.
Extending how many kilometers? Oh,
millions of kilometers.
So that's thicker than the photosphere. Wait, what was the last one you?
A few thousand kilometers thick.
And the chromosphere?
Uh-huh.
Chronosphere?
The chromosphere.
Chromosphere. Oh, so it goes photosphere, chromosphere, corona. Okay.
Yeah. It is visible during a total solar eclipse as a white halo. The corona has temperatures of about 1 to 3 million degrees Celsius. So the very outside is hotter than the few layers of the inside, and the core is the hottest.
Yeah, okay. That's interesting. Wonder why it gets hotter. And okay, and that's the last one, the corona. So basically, well, that's now confusing because I was going to say that the chronosphere, or whatever the one before, chronosphere? That sounds like time. A chrome.
CHROMOSPHERE.
Chromosphere. Okay. So I'm guessing we could say that the corona is like when you draw a picture of the sun, it's the little wavy, spiky part that you do.
Yeah, absolutely.
That's the corona.
That's the rays that hit us.
Yeah. Well, it's part of it. Part of that.
um, let's see.
I wish I could see the corona in a telescope. Why can't you see it? Because I guess it's not very thick. You can see it during an eclipse, is what it said.
It's the white halo around it.
Yeah.
That's all you see with the light. Well, we kind of are seeing it in like
In the video.
right here.
I
That,
guess
like,
you're
lighter
right.
spot.
Yeah, the gradient here around it.
Mhm.
Oh, well there you go. That's
That's what I
that's
was
probably what that is, huh?
assuming, yeah. As long as your lens is clean.
Yeah.
It's not a halo. So the core of the sun is about 20 to 25% of its total radius, which roughly translates to 140,000 to 174,000 kilometers.
Wow. The sun is huge.
Yeah.
I think I read that the sunspot that's on the edge there coming back into view was like I don't remember exactly, maybe 16 times the size of Earth. So it's massive. And it's teeny on the sun.
Yeah. You can barely even see it.
Yeah. Okay. Oh, the other thing I was researching is predicting the aurora, which is pretty tricky because it's, well, I don't know. It just is. but
Mhm.
some things we can see. I think we have some models, like scientists have some models that can kind of understand how the magnetic field of the sun works. But the most obvious signs are some of our some of the instruments that look at the sun can see when there's a flare, and a solar flare, like I think it moves really fast. I don't know exactly what it is. I know more what a CME is than I know what a flare is. I don't really know why a flare works the way it does, but I guess it's just like a little flash, a little bright light or big bright light. The CME is actual like plasma leaving the sun, not just light. It's actual, I guess plasma is like half gas, half solid, or what is a plasma? This is some basic science stuff that I have forgotten. Hi there, East Side Nutty. Nutty? Yeah, I said your name right. Commenting, hi.
Plasma is.
So we're looking up what plasma is. Thank you, Katie.
Of course. It's me in chat.
Yeah.
Chat. Plasma is one of the four fundamental states of matter alongside solid, liquid, and gas. It is often referred to as the fourth. Okay, that's four. Plasma is a hot ionized gas containing approximately equal numbers of positively charged ions and free electrons.
Okay. So essentially, we'll just call it really hot gas that gets flung off the sun. And so that, since it doesn't travel at the speed of light, because it's actually particles or physical, whatever matter, that it can take anywhere from, I think, a few days to like several days to reach Earth. And so that can kind of be tracked. And you can go to like just Google like the Aurora Borealis tracker thing, or like sometimes I'll look up a live view of the sun. There's some websites that have that, and it'll show different images. Some is like the visible light waves, some are other light waves, and so those are some ways you can track the sun, and that's why you can have an idea of when the Aurora Borealis will be more visible, because if you see a huge CME leave the sun, you may have a day or two before it actually reaches Earth. So
That makes sense.
yeah, but I don't think we have good enough models to predict when a CME will actually erupt.
Yeah.
We can guess because of what you're seeing now in this live stream, like those sunspots are active zones where there could potentially be CMEs, but I don't think we can actually know for sure when they'll happen. But these sunspots go away, right? They're not always there, and so they do give us a hint that something's up. Yeah.
Very cool.
Okay. Well, there you go. I think if we stay out here any longer, we'll probably get a sunburn because even though it's evening, the sun is still feeling hot.
Yeah, it's nice.
So, you know,
I'll
refocus.
share the chat screen.
Refocus. Hmm. So someday I would like to do this with like maybe constellations and like star clusters and things at night. Maybe find more interesting things with my camera.
Yeah.
But
We could have done the beehive cluster.
yeah, the beehive cluster is a good one.
We found that on the night of Aurora. So
Yeah, there are more important things. Got to see the aurora. All right. Well, thanks for joining me. Thanks for watching, everybody. This was fun. This is the sun saying good night. We got probably a couple hours before sundown, but anyway, that's all